Alrighty. So let's see. So this one's gonna be Physics 111, Chapter 8, which is gonna be your potential energy and the conservation of energy. And conservation of energy. Let's go ahead to our module. Let's open up chapter 8 module. All right, so last class, we actually talked a little bit about potential energy. We talked about kinetic energy. We actually touched up on potential energy. So, did anybody ever tell you that you have potential? So, the word potential means they have the ability to. So, the potential energy, now usually I go with PE. Potential energy. Now your book, he likes to go with U of X, which is the same thing. So you'll see P or U, the same thing. So there's the different types of potential energy. Okay, there's what we looked at last class was your gravitational potential energy, which you account for increasing energy for the kinetic energy that increases when you fall. Now we actually define the gravitational potential energy as your mass times your gravity times your height. There's also your elastic potential energy. That's better, I can find it now. Yeah. So, potential energy is the energy that can be used within the configuration of a system of an object that exerts a force on one another. Now, a system of an object may be Earth and a bungee jumper, gravitational potential energy, or elastic potential energy, which accounts for the declaration of a bungee cord. So, physics determine how potential energy is calculated, and it's account for your stored energy. Now, your potential energy for an object, again, U is the PE, is your potential energy, equals minus the work. So the change in gravitational potential energy is the negative the work done. So actually, let me just come over here. Now we define the work as your integration from last class, from initial decision to final decision, f of x, d of x. And we said that delta U, change in potential, I'm just following your book right now, change your potential energy, delta U is going to equal 0 minus your work. So that means that the change in potential energy is going to equal to minus the integration from x initial to x final, f of x dx. Now, we talked about gravitation, so when we talk about gravitational, that means, well, that's when your potential energy equals to your mass times gravity times your height. Okay. So we're talking about your force, where force is going to be your mass times your acceleration. Let me just write it down over here. So your force is mass times acceleration, which in this case, the acceleration would be gravity So your force is going to equal to your mass times your gravity. But you're going opposite of, let me go ahead and write this down. So actually, hold up. So this is going to equal to, your potential energy is going to equal to, now, on the horizontal axis, on the x-axis, you're not going to have any gravity. When you're talking about the y-axis, your vertical, that's where you're going to get your y. So your force, in this case, is going to be your mass times your gravity, which you're going against that, so be minus, and you're going in the y direction, so you're going from y initial to your y final. Now, solving this, what you're gonna have, you're gonna have your negative goes over the negative, so what you're gonna have your mg from y initial to y final, d of y for your height. Which is going to equal to your mg y, you go from y initial to your y final, which is going to equal to your mass times gravity times your initial height minus your final height, which is mg delta y. So your gravitational potential energy again is your mass. Let me go ahead and label these. Mass, gravity, which is your 9.8 meters per second squared, and your displacement. Now, when you're talking on for a spring, actually, let me just go ahead and just do this right over here. When you talk about for a spring, again, your potential energy is going to equal to your integration of minus the work. So that means your change in potential energy is going to equal to, now your work in this case, go ahead and get for spring, your force is going to equal to K of X, or actually minus K of X, where K is your spring constant and X, that's your displacement or distance. So that means, right now we're doing it for the spring. So that means delta U is going to equal to your integration minus 2 minus F of X d of X. Actually, let me just get this minus out. So that means this is going to equal to your integration for negative minus K of X d of X from X initial to X final. Actually, let me go ahead and take this down a little bit. All right. now solving for this one, your negatives go away, so that means your integration from your initial to your final. Your spring constant is a constant, so can go out the integration, which you get x d of x, which is gonna equal to your 1/2 k x squared from x initial to your x final. Let me go ahead and rewrite this down. So your delta u is going to equal to 1/2 k x squared from x initial to x final. So delta u, what's delta u? We said this is your change in potential energy. So your final minus initial potential energy is gonna equal to your 1/2 k x final squared minus 1/2 k x initial squared. Actually, let me go ahead also and put this down aside. It's too close to each other. Now, when you start from rest, that means your also potential energy goes to 0. That means your initial displacement is 0. That means your final potential energy is going to equal 1/2 k x squared. And again, k over here, that's your spring constant. So this is your elastic potential energy. Now, from the last chapter when we talked about an energy, we actually did a couple of examples on this. We talked about that in mechanical energy, your energy is going to equal to all your kinetic energies combined plus all your potential energies combined. And I'm just going to go with the kinetic energy as KE to differentiate it between it and the spring constant. So this is and again, that's your potential energy. Which what we can do, let me go ahead. So, you go ahead and just follow the book a little bit. So your energy, your total mechanical energy is all your kinetic energies plus your potential energy, U. Now, we said that the change in kinetic energy is going to equal to your work, and your change in potential energy is going to equal minus your work, your negative work. So this means that your change in kinetic energy is going to equal to minus your change of your work. If you actually substitute these two together. So what you're going to have, that means your kinetic energy final minus your kinetic energy initial is going to equal to minus your potential energy final minus your potential energy initial. Now let's go ahead and open it up. So what you're going to have, your kinetic energy final minus kinetic energy initial is going to equal to your potential energy initial minus your final potential energy. So let's just put all the finals together and all the initials together. What you're going to have, your kinetic energy final plus your potential energy final is gonna equal your kinetic energy initial plus your potential energy initial. And this is, ladies and gentlemen, what we call your law of conservation of mechanical energy, which again, from our definition, where your energy is all your kinetic plus all your potential. So this little fellow over here, that's gonna be your final energy. And this little fella, that's gonna be your initial energy, which means that the change in the energy is gonna equal the change in kinetic energy plus all your change in potential energy, which is gonna equal to 0. So this means that your energy again equals your kinetic energy plus your potential, or your kinetic energy is gonna equal your mechanical energy minus your potential energy, potential X. Oh, just write down potential energy, U. So basically, again, your change in potential energy is gonna equal the change of work, which is gonna equal to your minus F of X delta X. Or you can actually also say, when you get this continuous potential energy, that's gonna equal to du, I'll say du of X, is going to equal to minus the force of X dx. That means F of X is gonna be, well, for this one, for the instantaneous, this is the average. For this one, then the F of X is gonna equal to minus the change in potential divided by your change in precision. Same thing. So you have X is gonna be du of X divided by d of X. So let's say if you had an object. Let's say you have an object right over here. And you have a force going on the object going this way, which means you have a friction force going that way. Now this object it will have a velocity v. It will start as v naught initial and we'll go to final. So your force minus your frictional force is going to equal to your mass times acceleration. Now remember we said the final velocity squared from chapter number 2 is going to equal your initial velocity squared plus 2a multiplied by your distance. Now, if we solve this, we take this one and you solve it for a, what you're going to have? You're going to have phi final squared minus phi initial squared divided by 2 times D. Now, so we can take this little fella and plug it right over here. So what you're gonna have? Let me go to black. That means the force that we have minus the frictional force, FFK, is going to equal to your mass multiplied by your V final square minus V initial square divided by 2D. So what we can do, actually, we can take the distance out. So what you're going to have, you multiply both sides by the distance. So you get the force multiplied by your distance, FD, minus Fk of D is going to equal to your mass. Your distance is going to cancel out. So let's just leave the half one out. So VF, go ahead, VF squared minus mass over 2 VI squared. That means your force multiplied by your distance, D, is going to equal to, actually, let me take the parentheses out because I do not want anybody to think it's a variable. So let me just go put D over here and D over here, and let me go ahead and put distance, that's your D, which is those are your distances, right? So your FD, force multiplied by your distance, is going to equal to your MV final square over 2. Minus your MV initial square over 2 plus your frictional force multiplied by your distance. Well, actually look, this is going to be your final kinetic energy, and this is going to be your initial kinetic energy. With both of them coming in, this is going to be your delta K E. So your force multiplied by your distance is going to equal your change of kinetic energy plus your change in kinetic energy plus your frictional force multiplied by the distance. Which, if that happens, what would happen to you actually keep on going with the force? You're going to have a thermal energy. So this energy that you're going to have is going to be thermal. So let me go ahead. So basically, your force times this is going to equal to an energy plus your frictional force multiplied by your distance. You go change of energy. So your F of D. So the change in that energy is going to equal to when this is equal to 0, your thermal energy, go ahead and label it down. Is going to equal to that force. Black again. So your thermal energy is going to equal to the frictional force multiplied by your distance. Now go ahead and reapply this back over here. So that means your force multiplied by your distance is going to equal your change in the mechanical energy plus your change in the thermal energy. That means that your work is going to equal to all your change in your mechanical energy, plus all the change in the thermal energy, plus all the change in any internal energy. Now, in order for us to get to equilibrium, it has to equal to 0. So your delta E mechanical plus delta E thermal plus delta E all your internal energy is going to equal to 0. That means the change in mechanical energy is going to equal to negative change in the thermal minus the change in the internal. So this is going to be the mechanical energy 1, 2, final. Mechanical energy final minus your mechanical energy initial is going to equal to what? 2 minus delta, you change in the thermal energy plus any change in the minus the change in the in the thermal energy minus any change in the internal energy. That means your final mechanical energy is going to equal to your initial mechanical energy minus the change in thermal energy minus the change in any internal energy. Now, we also touched on the power last time. Which is the rate of doing work. And we define the power as your work over time. So your average power, again, is going to be your change in any energy divided by your time, where your instantaneous power is going to be your derivative of dE with respect to t. Let me go ahead and write this down. And that should actually close on chapter 8. So we went ahead, we derived the equations for the gravitational potential energy. We also derived the equation for the elastic spring potential energy. We also defined the mechanical energy, which is all the sum of all potential energy and all kinetic energies in the system. The work done by conservative force increases again, this K, the big K, that's your kinetic energy. So it increases your kinetic energy and decreases your potential energy by amount of delta K. E is going to equal minus potential energy. A change of kinetic energy is going to equal to change of potential energy. That means your final energy is going to equal to your initial energy. And that's where your law of conservation of mechanical energy comes in. We also define the force, which is minus du over x, and we write the mechanical energy as all the potential and the kinetic energy combined. So, because then only change transfers to the work, your work is going to equal your change in all your mechanical energy plus your thermal plus your internal. Now, for the power, we talked about power on chapter 7, a little bit more, but we can expand that definition of power. In general, power is the rate of an energy transferred by the force of one type to another. If an energy delta E is transferred in a time, delta T, the average power is delta E over delta T, where the instantaneous power is dE over dt. And that should close chapter 8. you have any questions, just email me at abunaem@uah.edu, or you can contact me at 256-348-1480. Thank you.